Hi everyone. In this lab we are going to do Lab 17 exploring solar panels, and we have a small solar panel here, and I've already set it up for us, and I've already zeroed and calibrated it and done the short circuit part. So I've got everything going here, but what we're going to do next is go through these procedures. Now I've done these parts here. It says take the equipment outside a place that will receive sunshine for the duration of the experiment. Well, it's pretty cloudy and cold here, so I'm not really sure it's going to work any good, but I'm going to do this like from my window. So we're going to position the solar panel so it is facing toward the sun, create a plan to investigate how current and voltage, blah, blah, blah. And so we've done this part already, and I am going to start collecting that data now. So hold on for that. So you probably can't see it very well, but I have a solar panel connected up here in my window next to my Batman statue here. Energy sensor, I have a variable load set to 70 ohms, and I am going to start taking data right now. Just on the sunlight from the window. And it's not a lot. I'm getting about 0.2 of a volt and 4.2 milliamps. And I'm gonna let that go for a minute. It says 30 seconds. I'm gonna let it go for a minute so that we have a little bit of time here. You can see the power and the current on one graph, and then the potential. So that's going. So at a minute, I'm going to take this out of the window and turn it on a lamp, which is a natural daylight lamp. It's a 100-watt lamp. Oh, sorry, no, it's a 60-watt lamp, not 100 watts. So then I will put this here, and I'm going to put this pretty close to it, and then we will turn this on. See if we can see a change. Definitely seeing a change. I'd say the potential has leapt up. It looks like we're at 2 volts, right, 10 times, and the current is 13.3 amps. So the power is going to be a lot of watts. Well, a lot of milliwatts. And that is pretty steady. This will allow us to get some values here. And 10 more seconds, I'll stop it. Okay, so stopping it now. And then let's take a look at our data. So looking at just the lamp, it has maximum current, maximum voltage. So let's go ahead and highlight. Well, let's start with potential for lamp. And I'll hit the statistics button here. And actually I will turn off the other camera so you don't have to be distracted. So we see that here for the maximum potential, which is the voltage in the lamp, it was 0.205. So we're going to go ahead and put 0.205 in our table, which is what you see right here. Then I am going to, sorry, that was the maximum voltage, 0.205 in the voltage column, not the current column. I'll fix that in a moment. And then we're going to go here and highlight the current, which is going to give us, and then I'll see the maximum for that, which is, it is 4.46 milliamps, we'll call it. And then I'll turn on, first I'll do, before I turn these off, I will do the sunlight parts. So sunlight's pretty steady, so it's not going to vary hardly any. The potential is, turn on the statistics, it's going to be The maximum is 2.21 for voltage. And for this, it does actually vary a little bit. There's noise in the system for the current. And that is a value of 13.83. In case you see where I'm writing this, I'll show you in a moment here. We have 13.83. And then under power, I'm just going to turn this to power. I'll turn power on and I'll turn current off. And then we can get the same values for power. So I'm going to just highlight this for sunlight and get statistics for power. And it is, the max is 30.27 milliwatts. So we're going to say 30.27. And then we are going to go to here and get the maximum, which is 0.914, a lot different. So these are our values right here. So now there's the second part of this. I've connected a light sensor, so I'm going to measure the light coming out from outside, and that's in units of lux. It's been calibrated. So we've got the second part here. I'm going to go ahead and start that. And I'm going to discard the other data. We should soon on our screen see my lux measurement. Here we go. It's a little noisy. Well, I should make it for a longer amount of time, so I will do that. Okay, so I will go to here, and I will make it for 300 seconds, just for giggles. And then I'm going to try it again. Okay, now we will see what we have. We have illumination coming in at not really high values. We have 276 lux. I'll turn this off if I get some shadow light from her. All right. There we go. And now I'm going to turn this over to my light here. We'll see what we're getting at this guy. See if it's any higher. Looks like it's 47,000, something like that. And then I will turn the lamp off and then come back down so we can, and I'll stop it. All right, so let's go ahead and check the mean values of our stuff here. I will turn off the camera. All right, so now you'll see that I filled out much of this table for you, and I've got, from our different runs, we did one with the sun. I'll just call this one's the sun run, and this is the lamp run. The power that we calculated, that we measured, is here, these values. And this is in lux, in illumination run. So that's just how much power we were, the theoretical power we're getting from the sun. If you divide this in lux by 75, you get the power in watt per meter squared. And that's what this second number is. We get the efficiency, which we'll get later, by dividing this by this second number and multiplying by 100, and you get it as a percentage. So the instructions will tell us here what to do, but what we did was the average power is, well, it's just whatever. This is kind of a little weird. I put both values here. It was only asking you, it was saying to do 2 runs at the same time. We just did one for each, the sun and whatever. So just leave this blank for now. Actually, just leave it blank. Here's what we're interested in. I'm just going to say blank here. Don't put anything in that. The number of cells on the panel was 8. Each one was 2.5 centimeters squared by 2.5 centimeters squared. So it was 6 1/4. So 2.5 times 2.5. So the total area is 50 centimeters squared, or 0.005 meters squared. I did that conversion for you. The power per square meter is 6.054 watt per meter squared. And that's just this value in 30.27 divided by that value. And then the power from the sun is the same value divided by, it's the sun's value divided by that area. Now, what did we do? To get the panel efficiency, I got 26.4% for the sun and 4.8% for the lamp. So how did that happen? I took this value of 3.45 watts per meter squared, which was 259 from the light. Remember, that was the light thing that I had. That you divided that by 75 to get meters squared. I divided this by that, multiplied by 100. That is basically how much power we got versus how much we theoretically could have gotten from that much light. And I did the same on the other. Now, for the sun, it was 26%, which wasn't terrible, but it was very low overall power, right? And then 4.8% for the lamp, which was a lot of it's lossy, right? It did not, even though the power went up considerably, remember that graph? It was more wasteful, right? Much of it was being reflected. The cells just couldn't handle all of that. What can you conclude about how distance affects how much voltage is produced? Well, let's just say that the sun's further away than the lamp. You would say that the distance makes the voltage go down. It's also cloudy, but just in general, distance makes the voltage go down. How do current values that you recorded inside and outside compare to each other? Now, we'll just say that the inside value, which was the lamp value, was a lot higher. Because we didn't do an inside light and outside light one because I wasn't going to go outside today, so just say inside was a lot higher. How do voltage values recorded inside? Inside was higher again. Calculate the power for the lamp in sunlight. Record the values in data. This is already done. You don't have to do that. If you had to choose to collect data inside or outside the sunshine, which would you choose and why? Well, normally you would choose it outside because normally there would be less filtering for the window. Just put outside because there's less filtering of the window. I mean, I'm going to understand when you write these observations and hear what the right answers are. So don't worry if it's confusing because we didn't do the lab exactly the way they recommended. And then here's how to do the efficiency. We talked about it already. Here's how the math happens. There were 8 panels. We got the runs recorded. We did one with the lamp and one with the light because honestly, outside was not going to be any brighter. Determine the power per square. We did that. And then here's the conversion I was telling you about for the illumination. So how does efficiency of your PV cell compare to your predicted efficiency? Well, we didn't do this, so don't answer that question. Don't answer this question. And what factors may contribute to the lack of efficiency of a PV cell? And that is, one of them is you reach a limit to what it can do. And then we have the reflectivity of the panel itself are two that can affect that. That's it. You don't have to answer all these questions exactly right because we didn't do the lab exactly the way that the lab itself suggested because, we're not in a lab and I'm not going to run around outside and have you do this. So if you answer the way I have instructed you here, you will get full credit. Hi everyone, so I hope you enjoyed the lab. I know we didn't follow it exactly right because it wants us to go outside and do sunlight and go inside and do sunlight, and so I did a lamp and the outside instead and the window instead, and that's the reason for the differences. Just if you just follow the instructions I had here, you'll get full credit, and I hope that you learned something, and I hope you had a little bit of fun. Would have been, of course, more fun if you could do it yourself, but maybe someday soon we'll have that. So anyway, take care. Ask if you have any questions. Bye-bye.